Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here for day 17, Advent to Code. Last couple days have been okay. I think not too bad. I feel like we're plowing through these. So yeah, keep your input, your comments coming, and thoughts and stuff like that. Love to see your solutions. We're just trying to improve ourselves so we can be, better at solving puzzles. And I think the best way to do that is to practice. So if you're watching this and you're like, oh, this is interesting, I wish I could do this type thing, best thing to do is just to get into it and start practicing. So with that being said, let's practice on day 17. So this one is 2 steps forward. You're trying to access a secure vault protected by a 4x4 grid of small rooms connected by doors. You start in the top left room marked S, and you can access the vault marked V once you reach the bottom right room. Okay, so here's the map. Got it. Fixed walls are marked with a hash, and doors are marked with a dash or pipe. The doors in your current room are either open or closed and locked based on the hexadecimal MD5 hash of a passcode, your puzzle input, followed by a sequence of uppercase characters representing the path you have taken so far. U for up, D for down, L for left, and R for right. Interesting. Using MD5s a lot here, huh? Only the first 4 characters of the hash are used. They represent respectively the doors up, down, left, and right from your current position. Any A, B, C, D, E, or F means that the corresponding door is open. Any other character, any number A, means that the corresponding door is closed and locked. Oh, I read that wrong. It's B, C, D, E, F, not A. Okay. To access the vault, all you need to do is reach the bottom right room. Reaching this room opens the vault and all doors in the maze. For example, suppose the passcode is HIJKL. Initially, you've taken no steps, and so your path is empty. You simply find the MD5 hash of HIJKL alone. The first 4 characters of this hash are CED9, which indicate that up is open, down is open, left is open, and right is closed and locked. Because you start in the top left corner, there is no up or left doors to open, so your only choice is down. Gotcha. Next, having gone only one step down, only gone one step down or D, you find the hash of HIJKLD. This produces F2BC, which indicates that you can go back up, left, but that's a wall, or right. Going right means hashing this to get this, and all doors are closed and locked. However, going up is worthwhile, even though it returns you to the room you started in. Your path would then be down, up, opening a different set of doors. After doing down, up, only the right door is open. After going down, up, right, all doors lock. Okay. Okay, so HIJKL doesn't have a valid solution. That's what it's saying. Because you'd go down, up, right, locked. Got it. Passcodes actually used by Easter Bunny Vault Security do allow access to the vault if you know the right path. For example, if your passcode were that, the shortest path would be down, down, right, 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 down. With that password having a different shortest path and this one having another shortest path. Given your vault's passcode, what is the shortest path? The actual path, not just the length. Okay, so you're giving the actual path, not the length of the path. So we need to track the actual path. And then this is my puzzle input. Okay. I think we've done things similar to this before. This is like this is a Dijkstra BFS problem. I think we just do a BFS here. The reason is, right, all distances are 1. So the question then is like, how do we calculate our neighbors? That's, you do the MD5 of your previous of this plus your previous steps, and then you add all the neighbors to the end, and we're just going to process them in BFS fashion, and when we find the first one, we're done. So we do need to keep track of our path because we're going to add that to our MD5, but eventually we'll have a path that puts us here. We should decide how we're going to represent this. We probably actually don't have to represent it. We just need to know what current room we're in, which like starts at 0, 0. And we want to get to 3, 3. So our initial state is 0, 0 with our password and an empty list of steps taken. And we call get neighbors, and that will tell us what our neighbors are. And we just update our state with the directions we've taken. And we know we're done when we hit state 3, 3. Again, to clarify the reason why this works, why like a breadth first search works for these like find the shortest path problems, is because you're always considering the shortest paths first. Remember, you're going wide first. So if you ever found, like if you'd gone like let's say it's 5 steps, you consult all the 4s, all the ones that are 4 steps, you don't find any, and then you go to all the ones that are 5 steps away and you try those 5-step ones. If any of those work, you know the path is 5 and you're done, so you don't have to go anymore. This one's an interesting problem because we know that we, like say for example, we know the length is 5. It wants the actual shortest path, which seems to suggest there is only one shortest path. If you're doing an actual breadth first search, there may be multiple 5s, right? And those may have different paths. Anyway, I think they may have different paths that all lead you there, but it seems to suggest there is only one, at least for our puzzle input. So again, I think we just do a BFS. We just need to track, we just need to figure out how to do our neighbors, given a state, and then we know we're done when we hit here. We'll have to figure out the MD5 stuff for our neighbors. Okay, let's get coding. What is our input? Our input is literally just a string. So we can just do stir like this, I think. And I am going to trim. Notice I had this little to-do to remind me. So we will need a state object. What is this called? Passcode. So we'll have a passcode. We'll have the directions, which will make a vec of cars. That's probably actually all we need for it. Oh, we also need to know where we're at. like that. So if we impl state, I can never remember exactly where you put those. Fn new. That. So let's create let's do like a neighbors function. Which is going to return a vec of self, I guess. So we first need to MD5. Should I just do this as a, because I think you have to pass it as a U8. So we do that. And we want to update it with, oh, I need it myself, I guess. Self dot passcode. We want to should I actually should do this as a U8 as well. So then I can just then also do hasher update. We need to format it, right? Is it finalize? We've done it so much, I feel like I've figured it out. So I guess I don't need this anymore. Okay. I think it's like that. So now what do? We want to determine if we can go up, down, left, and right. So we can say like if self.locate location dot 0 greater than I'm gonna do this. That's probably gonna make it easier to parse the stuff. So we'd say if location self dot x is greater than 0, and okay, what are these positions? The doors up, down, left, and right from the current position for the first 4. Can I do that? So I do and hash z. Okay, we're trying to determine if we can go up, so it's actually y. All right, those are the B, C, D, E, F. I guess instead of good, I can call open. So what I'm trying to do is like say like open dot contains hash 0. This means it's both open and I'm not at the bottom, so I know I can go down, or I know I can go up. So neighbors dot push self x self dot x y, oops, self dot x y self dot y minus 1. Clone the passcode, and then the directions equals I guess I have to push like that. Oops. Like that. What doesn't? Oh, I can do this. Okay. So that's up. So I just need to do the same for down, you know. Right, 3, 0, 1, 2, 3. 0, 1, 2, 3. So if I'm at 3, I can't go down. Up, down, left, right is the order we want to do it. So 1, down, plus, same thing. We do left. Where it's got, so it's got to be greater than 0, and our hash is 2. We want to go left. So -1, right? Okay. Up, down, left, right. We're going to plus. Okay. So I think that's our neighbor's function. The idea is we're just going to see, you know, make sure we aren't going to go out of bounds. And we have one of these things and we're going to add them to our neighbors. Okay. So let's just do the BFS. Oh, I guess I want to do an initial state. Is that how I did it? Oh, I'm not going to return the usize. I'm going to return a string. So this should be a string. So now I'm going to have let start, I guess. So we'll go, oh, I'm going to have to import some things here for state, or derive them, I guess. Debug clone hash eq partial equal. Is that enough? I think so. So let frontier equal vecdeck. I don't know why I'm blanking on that. New frontier dot pushback start dot clone. Let me visit. I'm missing a visited equal fx hash set default visited dot insert start dot clone. Now we're just gonna, so these are our visited list and our frontier list, and now we just do like the while let sum. Fronties. No pop. Front. So in this loop, we're going to say if state equal state dot x is 3 and state dot y equals 3, return state dot directions. So it's a U8. Iter dot map C or B as car dot collect. Okay. What did I hit the unreachable? Probably, yeah. So that's our check. Did we find it? We'll also say, so now we need to do our for neighbor in state.neighbors if visited.insert. So it returns true the first time. We want to, so if we have a new neighbor, we want to add that to the list. So frontier.push back neighbor. Like that. Okay, that's my answer, but I actually want to test some of these cases just to be sure before I submit. Config test. So we say let state equal state new. This one. And assert equal BFS state. This. Let's see. Go to advent of code. It's that one. And then we overlay use AOC test 17. Oh, I think it's test. Okay. Should we do one more just to be safe? This one looks like it's a longer one, so maybe we do this one. It's going to be this. Okay. One more, please. Yes. Okay. So I feel pretty confident this is the answer. That is the right answer. Okay. Not too shabby for part one, just a BFS. For part two, it's you're curious how robust this security solution really is. So you decide to find longer and longer paths which still provide access to the vault. You remember that paths are always end the first time they reach the bottom right room. That is, they can never pass through it, only end in it. Okay, so like it's like longest path, but you got to stop at 3-3. If your passcode were blah, the longest would be this. If your password were this, the longest would be this, so on and so forth. What is the length of the longest path that reaches the vault? Okay, so this is like, I think, if you look at the original Dijkstra's algorithm, it actually calculates like the shortest distance to like every path. If you look at like BFS implementations, like mine, for example, we short circuit where the state is equal to 3. Right, we know we're done, so we return. You can do what at least I've usually heard called like a BFS all, and that will give you like all of the paths, or all of them that are equal to 3, all of them where this thing is met. So basically, you don't return here. If you ever find one that's 3-3, you're done in that path, but you can add it to like your list of things, right? And so we can do like a quote unquote BFS longest, where we do this, but we calculate every single path, BFS all of them, and then every time we get one of these, we just go past it. So I'll show you what that looks like. We'll do this for part 2. We'll call it BFS all, and we want to return a usize. So this is BFS all state 0 0 input. That, yeah, we're not there yet because we're returning the wrong value. So we just say let max equal 0 or something like that, and then we say here we'll continue in our thing, but we'll say max equals max dot max of state dot directions dot lane. And then here, it's no longer unreachable. We just return max. Okay, there you go. 384. There you go. Part 2 in the bag. Okay, this day wasn't too tough, right? It was just, I think even in this year we've seen this where we're just doing BFS to find like the shortest path because the distances are 1. And so the tricky part is how do you figure out your neighbors, right? So in this case, I maintain my state with my location, my passcode, and then the directions that I've taken, because those are all needed to derive my neighbors. But they're also like what makes it unique, right? So I know if I've visited it before, I shouldn't add that neighbor in there. I shouldn't continue down that path because I've already gone down there. It doesn't take terribly long. I'm kind of interested in the BFS all to see how many total states there are. There must be something about how the MD5 computes them that gives them a small thing. Normally a BFS all can be really bad for extremely large like graphs because it's kind of explosive, right? So especially if there aren't limiting options. So it's clearly how the MD5 calculates the neighbors that like limits the number of options you have once you go down a path. So we do let moot paths equals 0, paths plus equals 1. Then we can just down here we can do print line paths like that. Okay, yeah, so there's only 1,300 total. So we had to do 1,300 paths, and only 384 of them like led us to the end. So, okay, not too bad of a day. Like when you're thinking about optimizations, there's probably not a lot that you can do here, just because we already know how to solve these problems. I think like you just BFS and then you BFS all, right? And I wonder if you could make these things more like, could you do state.neighbors dot iter dot filter Yeah, I mean, this gives you the same answer. Is this better than like this? I don't know. Like, I mean, I don't know why that wouldn't work, but like, which of these do you prefer? I don't know the answer to that. And it's hard to say that it makes it any faster. Because there's so few of these too, I think parallelizing, I don't know how much that's going to help. Probably what's going to speed up the BFS all the most is your neighbors function. So computing the hash faster. Yeah, the reason why, just too, as I'm looking at this, the reason why I did the unit tests is I didn't want to get like these things wrong. So doing like the testing, I think was helpful, just to make sure I don't, because I've gotten these things wrong before, right? This one wasn't too hard, but you know, sometimes you miss a up, down, left, and right. Okay. Yeah, I mean, I don't know what else to say about today. It was a BFS. If you know how to do BFS, it's probably pretty easy. Part 2, I mean, even if you didn't know about just like BFS all, you could probably infer it just by thinking about it a little while. BFS is definitely a thing to keep in your toolkit though. Gets used a lot in these puzzles. So definitely something to think about when you're like, oh, do I want to do this competitively or whatever? Be sure that you know about, Dijkstra, BFS, DFS, and like when to use the different ones, right? So we've done puzzles in previous where DFS is better because we want to like drill down to a position. And like so we can prune away things, whereas BFS is we just like slowly want to like work our way through the frontier, the edge, until we find the right thing. So anyway, those are things to think about. Otherwise, today's in the bag. So thanks, everybody. We'll see you next time. Bye.